In this lecture, we will be talking about scaling, which is an important practical issue related to filter design. There are two types. Okay, one is the so-called magnitude scaling, where the purpose is to bring the parameter values to practical range without changing the transfer function of our filter. Okay, so the purpose is to bring the circuit element values such as resistance, capacitance, and inductances of our components to practical ranges without altering the transfer function of the filter. Here we are implicitly assuming that our transfer function is unitless, okay? So it's voltage over voltage or amps over amps kind. Okay, so this is how we do it, okay? Let Km be our magnitude scaling factor. Okay, and after the parameter values are scaled with Km, they become the following. Okay, if you have a resistance in your circuit, then after the scaling, the new resistance of that resistor becomes Km times R. Okay, and we have L is changed into Km times L. Okay, so this is the new inductance. And as for the capacitance, we have C over Km. Okay, note that after these transformations, all the impedance values, okay, of our resistors, inductors, and capacitors, they change by a factor of Km. Okay, and then if, let's say, we're obtaining the transfer function as through some voltage division, okay, so it's certain impedance divided by the input impedance, then clearly that scaling of the overall impedances throughout our circuit will not change the transfer function. Okay, so after this change, let's see what happens. ZR J omega. Okay, so this is the impedance of our resistor, whose resistances are in the first or the initial design. Okay, so we know that it's frequency independent and it's R at all frequencies. And as for the impedance of the inductors, what we have is J omega L and ZC J omega is 1 over J omega C. 1 over J omega C. So these are the initial impedance values, and then after scaling, the new values become the following: ZR J omega. So this hat, suppose, indicates that these are the impedances after magnitude scaling. So ZR hat J omega is Km times R. Okay, so that equals Km ZR J omega. Okay, Km times the old impedance or the initial impedance, and Z hat L J omega is J Km omega L. Okay, omega Km L, and Z hat C J omega is 1 over J omega C hat, which is C over Km. Okay, therefore, in terms of the initial or the old impedances, we have Km, ZL, J omega, and Km, ZC, J omega. So after this modification to parameter values, what happens is the impedance values are all raised or lowered by the same factor, and that factor we're calling the magnitude scaling factor. And as we said earlier, if your transfer function is like you obtain it through some voltage division, okay, some impedance divided by the input impedance seen by the driving point impedance seen by the input, then clearly those Km's will cancel and you obtain the same transfer function, okay, as a result. So there's another type of scaling, and that's called frequency scaling. This time what you do is, suppose you obtain your transfer function and you obtain, let's say, the gain characteristics of your filter. So the gain versus omega, and through frequency scaling what you can do is you can squeeze that characteristics, or you can stretch that characteristics, and you can do that by again playing with the parameter values, and this is, we'll see how it's done soon. So here the purpose is to modify the frequency characteristics of a filter without introducing any qualitative changes to it, that is, without altering its type and properties such as H, J, omega max, or H, J, omega min, or perhaps quality factor. Okay, and so on. So how the scaling is done is as follows. Suppose Kf indicates our frequency scaling factor. Okay, and suppose that R, L, and C are our initial resistance, inductance, and capacitance values. So after the scaling, what you do is, or through scaling, what you do is, first of all, you don't touch the resistance values, okay? They're the same before and after the scaling. As for the inductance and capacitance values, what you do is, you scale them by a factor of Kf, okay? So let's see what happens to the new impedances in our circuit after the frequency scaling. Okay, let's begin by writing the impedances again: ZR J omega, ZL J omega, and ZC J omega. Okay, so this is R, this is J omega L, and this is 1 over J omega C. And then you apply the frequency scaling procedure. You change the parameter values as such, and then those new parameter values produce new impedances. And those impedances are ZR J omega, ZL J omega, and ZC hat J omega. Okay, since we didn't touch the resistance values, ZR hat equals ZR. Okay, so that's R. As for the impedances of the inductors and capacitors, what we have is J omega L over Kf, and here 1 over j omega c over kf. Okay, and that in terms of the old impedance values produce the following: ZRJ. Okay, let's leave that to the last part. What we have is ZL J omega over KF. Okay, so that's the new impedance. And what the new impedance is, it's the old impedance where the frequency is scaled. Okay, likewise we have ZC J omega over KF. As for ZR hat G omega, it equals ZR G omega, but since the impedance of a resistor is frequency independent, there is no harm in writing ZR hat G omega equals ZR J omega over KF. So the conclusion is that after frequency scaling, all the impedances are scaled in the following sense. Okay, and that produces the effect on the transfer function of the filter, such as squeezing the shape, okay, the gain characteristics, or stretching the gain characteristics. Note that while squeezing or stretching, things like the maximum value or the minimum value, they don't change. But what changes is the frequency at which the maximum is attained, for instance. Okay, let's say the center frequency for a bandpass filter. Okay, now this is magnitude scaling, this is frequency scaling, and let's apply this pair of procedures to an example filter design. Okay, consider the following bandpass filter. LCR plus minus V in, and this is where we collect the output. Okay, V out. So for this filter, we have the following transfer function: H of S equals R over L S squared plus 1 over LC. Okay, and in terms of our prototype bandpass filter notation, this corresponds to Ks S squared plus 2 alpha omega 0 S plus omega 0 squared. Okay, omega 0 is 1 over squared of LC, which was our center frequency for our second order bandpass filter. Okay, suppose that we designed initially our filter by the following parameter values. Okay, L equals 1 over 5 Henrys, C equals 5 farads, and R equals 1 ohm. Okay, so these are our initial design parameters. Okay, so with initial design parameters, what we obtain are the following: H of S is 5S over S squared plus 5S plus 1. Okay, and that transfer function produces the following properties for our filter. Omega 0, the center frequency, is 1 over square root of LC, which is 1 radians per second. And then bandwidth, which is R over L, okay, or 2 alpha omega 0 in terms of the prototype parameter values, which is 5 radians per second. And the quality factor, omega 0 over B, is 1 over 5, okay? Since it's less than unity, we're talking about a broadband filter, okay? Now, what we want to do is we want to change our initial design without qualitatively changing our filter, but changing it quantitatively in the following way. Okay, so we're asked to scale the circuit so that the new resistance value okay, well, initially your resistance value is 1 ohm, so it's not really a practical, not in practical range. Usually the resistance values are in kilo ohm range or sometimes even larger. Okay, so scale the circuit so that the new resistance value is more realistic, namely it equals 10 kilo ohms. Okay, and the new peak frequency okay, the frequency where the maximum value is attained, in other words, the center frequency, is 10,000 radians per second. Okay, it is omega 0 nu, 10 to the 4 radians per second. Okay, so we have to do both magnitude scaling and frequency scaling. Okay, so let's do it, but in order to be able to do it, we have to figure out the scaling factors, okay? So here is our scaled circuit. Okay, plus minus V in, plus minus V out, and here we have the new inductance value, the capacitor with a new capacitance value, and likewise for our resistor, okay, which we're labeling L hat, C hat, and R hat respectively. Okay, now L hat, note that we have to apply both magnitude scaling and frequency scaling, therefore L hat nu must equal Km over Kf times the initial or the old inductance value. C hat equals 1 over Km Kf times the old or initial capacitance value, and as for R hat, we have the magnitude scaling factor times the old or the initial resistance value R. Okay. Now, let's proceed with our design. Not really design, but let's continue with our procedure. So what's the new transfer function after scaling, which we're denoting by h hat of s. Okay, so let's figure that out. H hat of s equals r hat over l hat s over s squared plus r l hat s plus 1 over l hat c hat. Okay, so that in terms of the old parameter values and scaling factors produce the following: r over l kf s squared plus r over l kf s plus kf square 1 over lc. Okay, all we did was replaced l hat, c hat and r hat with their scaled with their expressions in terms of the scaling factors and the old parameter values. And then this h hat of s can be written as r over l s over kf. If you will, you can call it s hat. Okay, and then s over kf squared plus r over l s over kf plus 1 over lc. Okay, now that in terms of the old transfer function h hat of s can be written as h of s kf. Okay, now so what we have is, let's rewrite it, r over l kf s squared plus r over l kf s plus kf squared 1 over lc. Okay, so that's our new transfer function h hat of s. Okay, we just rewrote this, and that equals s squared plus 2 alpha omega 0 hat s plus omega 0 hat squared. Okay, note that after the procedure the damping factor alpha doesn't change. Okay, so this here 1 over lc equals the square of our initial center frequency or initial peak frequency. Okay, and then initial peak frequency squared times kf squared equals the new peak frequency squared. Okay, and from there we can figure out the magnitude, frequency scaling factor. And from this relation we have R equals 1 ohm and we have the desired new resistance value. Okay, we can figure out the magnitude scaling factor, and then once we have kf and km we can compute L hat, C hat and R hat through those expressions. So therefore we're done. Basically kf square omega 0 square equals the new peak frequency square. Okay, so that implies that the frequency scaling factor should be chosen as the desired new peak frequency over the initial peak frequency, which is 10,000 over 1. Hence our frequency scaling factor should be 10,000. Also R hat equals km times R, therefore km should equal the desired new resistance value over the initial resistance value R, which is 10,000 ohms over 1 ohm, which produces the magnitude scaling factor equals again 10,000. Okay, so let's check our circuit after these modifications. So finally we have the following. V in, V out. So the new inductance value is Km over Kf times L. So Km and Kf, they happen to be equal to one another. Therefore, L hat equals L. Okay, after the scaling, the inductance value hasn't changed. So it was initially 1 over 5 henries. So after the scaling, it's still 1 over 5 henries. How about the capacitance value? Okay, so it was initially what, 5 farads. Okay, and then the new capacitance value is 1 over 10 to the 8. So that produces therefore 50 nanofarads for our new capacitance value. And as for the resistance of our new resistor, it's initially it was 1 ohm and now it's 10,000 ohms or 10 kilo ohms. Okay, 10 kilo ohms. So this new circuit produces the following transfer function: 5 times 10 to the 4 s over s squared plus 5 times 10 to the 4 s plus omega 0 hat squared. Okay, hence the new center frequency is this number square rooted, which is 10 to the 4 radians per second as desired. The new bandwidth is 5 times 10 to the 4, okay, this thing here, 5 times 10 to the 4 radians per second. And as for the quality factor, okay, omega 0 nu divided by the bandwidth, new bandwidth, it equals 1 over 5. Note that the quality factor hasn't changed. It equals the initial quality factor.